Oh, that's burnt up.
Tanner, check Tanner, check Tanner, Tanner, check Tanner, check Tanner. Hello, this is Tanner Tech.
And today, we're going to be taking a look at an interesting problem with this fan. So this is a special kind of fan that can be controlled with a wireless remote. So as you can see, if I turn this on, it'll activate the fan blades. Now, one cool aspect of this is that it can also be controlled with an Amazon Alexa via this device that is able to send out the same signal this remote control sends. It is also connected to the internet. One thing this also does is you can press the button and it will turn on and off the light here. But as you can see, if I press this button, the light does not turn on, even when I pull this string. Now, earlier today, this light was consistently staying on. It wouldn't turn off. It was just continuously in the on state. And then when I pulled this out to take a closer look at it, I saw some smoke come out of this control device here. And then when I pulled the drawstring to manually turn on the electricity to the lights, I saw some sparks fly out of this. It was crazy. So I took this off and took a look at it. When I plugged it back in, there were no more sparks. It just stays off right now. So let's pull this thing off and take a look at the control circuitry that drives this and see if we can perhaps fix it. Let's take a look. Alright, so here we have the innards of this bottom part of the ceiling fan. This contains the 4 lights, as well as the 2 pole switches, as well as a couple of different run capacitors that run the fan. We also have this box that's giving us the problems. And this box is solely for the control of the lights in the circuit. I followed some of the wires here. We have 2 neutral wires. We have a live wire, and then we have a light out wire that's controlled, that turns on and off the lights. So the electricity flows in from hot, and it flows out through the red light wire to the different lights. Now, let's pull this apart and see what the problem could possibly be. I'll just use a screwdriver and pull off this bottom part. Oh, pulling this apart, I can already smell the magic smoke that comes from when components burn up. So it looks like this metal piece right here actually doubles as a heatsink. See, we have a piece of thermal silicone as well as some thermal paste that pushes into this metal part of the aluminum. So it looks like this is to radiate some heat. I'm assuming that that is from whatever is controlling the electricity in there. Since I didn't hear a relay click when this turns on, I'm assuming it's something silicon, like a triac or a silicon controlled rectifier. Let's pull this out and see what it is. Oh, that's burnt up. Alright, so this is the insides of the circuit. I'm not sure if you can see it well, but this SCR in here is completely fried. And the reason I know it's an SCR is because on the circuit board, it says SCR right there, which means silicon controlled rectifier, which is kind of interesting. I expected there would be a triac in here, but I guess this works. You can see that the solder is melted around here. There's some beaded up solder. And this white part on the case is not thermal paste, but it's actually where the case melted a little bit. You can see it's melted down here. So this part definitely is in the wrong. Now you may be wondering why there's so many big capacitors inside this circuit and resistors, and the reason why is so that way it can step down the 110 volts AC onto a more usable voltage of around 5 volts DC for this circuit to use. There's also this little blue disc in here, which is called a metal oxide varistor, or an MOV. And these are really cool. It's a type of device that actually changes its resistance with the voltage applied to it. So when it's at a usable voltage, like 110 volts, this thing has an almost infinite resistance. But when the voltage climbs higher, let's say if there was a power surge, then the resistance of this device is going to go down, causing it to short out and blow a fuse. And it's going to blow a fuse before it actually blows the circuit. Not really relevant, but just something interesting. So I'm pretty sure the problem is with this silicon controlled rectifier. So let's take a little look at how these things work. So here I've drawn out a few things, including the circuit diagram symbol for a silicon-controlled rectifier, like the one in our circuit. So the circuit diagram symbol sort of looks like a diode symbol, with this extra little wire coming out of it called a gate. And so basically what this device functions as is it's a diode or rectifier that can be controlled by a gate, hence the name silicon-controlled rectifier. So what happens is when there's no signal applied to the gate, then no current is going to flow through this diode, either forward or backwards. Then when you apply a small signal to this gate, it's going to allow current to start flowing through the rectifier. And then once the current starts flowing, if you take the voltage off the gate, it's still going to be flowing. The current's still going to be going through it. And the only way to interrupt the flow is to give a momentary stop of the current flowing through this device. If you stop that current even just for a small moment, then it'll enter its shut-off state. And then you'll have to put some more voltage on the gate in order to get it started again. So this is structured in a little bit different way than most transistors are. So most transistors, are either PNP or NPN transistors. But a silicon-controlled rectifier is PNP-N. So you can see that it contains actually both kinds of transistors, a PNP and an NPN, just kind of staggered. So down here is a little schematic that makes this a little bit more easy to understand. So here we have a PNP and an NPN transistors, hence the PNPN junction. And in this state, nothing's happening. Now when you apply current to the base of this bottom transistor, it's going to allow current to flow from the collector to the emitter. Now when that happens, it's going to start current flowing from this emitter through the base, which is going to turn on the top PNP transistor, which is going to let current flow from this emitter to this collector and into the base of this transistor, which is going to furthermore keep it on. So when you remove electricity from this point, then this circuit will still be active and current will still be flowing through here. So why use a silicon-controlled rectifier in a circuit as opposed to using a MOSFET or a normal PNP or NPN transistor? And the answer to that lies in some of the certain characteristics of this device. The first one being that it is very efficient and has a very low power dissipation. Once the circuit is activated and it's latched, it's going to have a very low internal resistance, and so you can have a very high voltage and even a very high current flowing through it. And it's not going to dissipate that much heat. It's going to let a lot through. And the other types of transistors, they have a higher internal resistance when they're on, and they're meant more for amplification, whereas this is really solely meant for switching. Another reason that these are used are because they work really well for AC applications. I was saying before how when this is activated, it needs that brief off pulse to reset the gate, so you can once again put a gate pulse on it. And that comes from AC. So when AC is in the positive side of the waveform, you can switch it on and off. You can use the gate and activate this diode for that positive half. But when it goes to the negative half, not only does no current flow, but it also resets the gate. So when the waveform comes back to the positive half, it can once again be turned on. So these devices work very well for handling AC applications. And if you really want to take all of the AC instead of just taking a half waveform, you can get something called a triac, which is basically two of these put together. That with one gate you can control the electricity flowing not only in one direction, but also in the other direction. So it allows you to use the entirety of the waveform. So these devices are really cool, and they've been very interesting to me. So I'm going to replace the silicon-controlled rectifier in that circuit with this. Now, this is just one that I had in my drawer. And if we look on the data sheet, it's called a TYN625. You can see that we have that same circuit diagram for it. And it's got a few different characteristics that will work well. The first one being that it can handle a 25 amps through it, which is a lot of amps, and I'm definitely not going to be drawing that much through 4 light bulbs, but it should still work very well for that purpose. Well, now it's time to desolder this broken component. So I finally have this silicon controlled rectifier removed, which proved a little bit more problematic than I thought, as the heat that it was exposed to caused it to break apart and crack. You can see some effects of that also on the circuit board. It's very much so blackened. Now, when installing this new SCR, you may be wondering why I'm not going to be using another SMD or surface mount deposition SCR. And the reason is, well, because I don't have one. And I also think that this larger SCR in a different package should work just fine. With the new SCR securely soldered into place, paying special attention to the pins to make sure they go in the right places, I think this is ready to test. So I'll put this back in the case and plug it into the light. We'll see what happens. Alright, so in an interesting turn of events, I've learned this box was not, in fact, the problem. And it wasn't even what I thought it was either. So I thought this box was something that when you press the button on the remote control, this would turn on the lights, because this is between power and the lights. But I realized that I'm actually wrong here. So this box isn't what it seems. The real problem lies in this box, the real light and fan controller. So what happens here is this is something called a wattage limiter, and it's not really that cool. What happens is it's constantly measuring the current flowing from the power source to the 4 light bulbs installed in this fixture. And it's meant to regulate these light bulbs under 300 watts. So it can calculate the amount of wattage that's going through here because it knows the voltage, which is 110 volts, and it knows how much current is flowing through here. So basically what this does is if it draws more than 300 watts, it shuts off the light bulbs, or it dims them. Now I've found 2 different opinions online about what this wattage regulator box might have been put in here for. One of those reasons may have been to keep this from drawing too much current, because if you put too much power going through the circuit, it could potentially blow it out. And the other reason is because in 2005, the government put out something called the Energy Protection Act, and it was meant to save energy. And so I've heard that this may have been mandated by the government, so that way you couldn't put high wattage bulbs in your ceiling fan light fixture to stop drawing too much current. Now, as to what the real purpose of these might be, I still am unclear. But what I am going to do is I'm going to remove this device, because I'm putting LED bulbs in here now, and they don't draw too much wattage anyway. And also, this thing is definitely burned out. After I installed this new silicon controlled rectifier, I looked in here and I saw another resistor burnt out. Now this resistor actually goes to the gate of the SCR. So it looks like what happened is when the SCR burnt out, it also took this resistor with it. And potentially this little integrated circuit down here that helps with measuring the wattage and controlling it. Now what's interesting here is not only did this SCR, when it blew out, take out this part of the circuit, but it also took out this, because the wire that goes to the lights from this remote controlled box is consistently staying hot. It won't turn off. And so it caused a cascade effect that hurt this thing as well. So let's take a look at this and see if potentially we can identify the problem in here. Alright, let's have a look under the hood of this thing. So first of all, one thing interesting that I noticed is when I took off the plastic case, lo and behold, was, oh, that was my multimeter. But here's a little piece of burn mark. So if I flip it over and match it to where it was with the burn mark on the case, you can see that the burn mark covered this section of the circuit board. So this section of the circuit board got pretty hot. Looking over here, you can see that there was nothing less than this red capacitor that is completely black. So that one's probably bad. As well, we have a silicon controlled rectifier. And this one is connected directly to this red wire that goes out to the light. And I just checked the continuity between this silicon controlled rectifier on the anode and the cathode, and yep, there's a short. So this silicon controlled rectifier is bad. Now I looked at the part number and I couldn't find any data sheets on it. But oddly enough, when I looked it up on Google, all I found were pictures of similar silicon controlled rectifiers, but none of them with the same part number. So that was interesting. But this is definitely a silicon controlled rectifier, and I think the same one that I used as a replacement in that other device should do just fine in here. So I'm going to take this silicon controlled rectifier out and resolder in a new one, and also resolder in this new capacitor. Well, that may have been my last little bit of soldering for tonight, because my soldering iron took the turn for a worst. I was in the middle of desoldering that capacitor, when all of a sudden, the tip of my soldering iron just snapped clean off. So given that my current soldering iron is out of the picture, I have to use this old soldering gun. Literally a soldering iron in the shape of a gun. And this one is only 30 watts compared to my original 35 watts on my other soldering iron. But you can see here that I've done a couple things on my circuit board. I've replaced this capacitor, which is 47 nanofarads, replaced it with a new one, same voltage rating, and I've replaced this silicon controlled rectifier with a brand new one. Just two easy component swaps. So now I'm going to hook this up to my Variac and just a simple light and see if I can get this thing to turn on. Oh yeah. So I got it working. So we have the Variac over there. It's supplying power to the board, and I've got this little tiny lamp hooked up to the end. So check this out. I press the light button, and it comes on and turns off as it should. So that new SCR in there is doing its job perfectly, as well as the new capacitor, and this board is now functioning as it should. So I'm going to put this all back together in its case, and stick it back in. Well, I've made a big mistake. I was just about done putting the fan back together when I dropped the screw inside the fan motor. There it is. Magic screwdriver with a magnet on it comes to a rescue again. Let's put this up once and for all. Well, at long last, the fan finally works. As you can see, the lights turn on as they should, and the fan can even turn on. If I ask Alexa to turn on the lights, Alexa, turn on computer room lights.
I'm having trouble connecting to the internet.
She doesn't connect to the internet. Well, that's nice. Anyway, thank you for watching, and stay tuned for next time.